Welcome to Module 3 of the Organic Chemistry class, but more than that, welcome to Organic Chemistry. Now, the reason that I say this is because the first two lecture modules that we talked about, all of that was regarded as review information, folks. All of it was supposed to have been taught in your general chemistry class, and that's the way that we start off on this course because we have to make sure that you understand those basics before we go further. So this truly is the first organic lecture that you're going to have. Everything in this module, it's not going to be sprinkle of new information. It is going to be a flood of new information. Now, the reason I say flood is because it's going to seem like a lot. And quite honestly, it is. However, it's just like a math course. If you figure out the procedure and you stick to the procedure and you do it the same way every single time, folks, there's a chance that you might not even have to study for a test because that procedure is going to stay true for almost everything that we do. Now, did you catch that word? Almost. Yeah, just like all the other science courses, maybe even a math class, there is an almost that gets introduced into these sentences because there's always exceptions, right? And we don't like exceptions. I try to stay away from the exceptions when I can, but there's only so much that I can do. So there's going to be times where the procedures don't quite match every single thing that we need to talk about, but I try to limit those. I don't want to introduce too many of those because when I do, this whole thing gets out of hand and it gets very, very confusing. All right, so I need to go through and give you some background about organic. I know that we've done that a little bit with Voller and the synthesis of urea and this idea of vitalism, some acid-base theory, drawing reactions and curvy arrows. But folks, again, this is full-blown organic now, so I need, once more, be like Anna, go back to basics, and we need to talk about a few definitions before we go further, all right? So the first word that I want to introduce to you in the language of organic is this word called nomenclature. All right, so nomenclature is just a fancy word. That's all that it is. And this fancy word means naming. That's all. You know, we use these words to make ourselves sound smart. We might not be smart, but if we sound smart, people will think that we're smart. So we use nomenclature instead of the word naming. So we're going to be talking about the nomenclature of organic compounds in this lecture, aka we're going to learn how to name. Now, which ones sounded fancier to you, right? So when you have a conversation with someone, tell them, oh no, we're talking about nomenclature at this time. Don't say we're learning how to name things. Complete night and day, but it's the same word. That means it's the same meaning, just with different words. All right. So nomenclature is what we're going to be focused on, and we're also going to learn how to draw. And I know you're probably looking at my handwriting and saying, well, how did he even pass organic? And let me tell you something. That was a struggle back in the day for me to draw and write so people could read it. Please give me a break. I barely made it through alive. All right. So when we name and when we draw, we are going to focus on one group of organic compounds. And this group of organic compounds that we're going to focus on is going to be called the group of alkanes. That is a K-A-N-E-S, alkanes. And this is our first section or grouping of organic compounds that we are going to be focused on. Now, we have to figure out, well, what classifies it as an alkane, right? So if we go through this process and I'm expected to follow the rules of alkanes, we have to understand what an alkane is first. And sometimes they're not going to just full-blown tell us it's an alkane. We're going to have to make that determination. Well, alkanes are very simple. Alkanes are very easy to pick out because alkanes are true blue, what we call hydrocarbons. Now, hydro, think of hydrogen, Hopefully you can see the word hydrogen in hydro. And carbon, of course, means carbon. Folks, it can't get simpler than that. So whenever I look at a molecule, and this structure includes just hydrogen and just carbon, there is a possibility that it's an alkane. I'm getting closer, but it's not quite fitting the definition yet. But this has to be a requirement. So if I go through and I add things like oxygen and nitrogen and sulfurs and maybe phosphorus, if I add any of those, it's not an alkane. It has to be just carbon and just hydrogen to make it fit this definition. All right, now that definition is going to get a little looser. Remember, I told you exceptions. Sometimes we smudge the lines a little bit. Sometimes we go through and we talk about all these procedures, and then like around the corner, we change the rules on you again. So this is one of those rules that could be changed, but once more, in the beginning, we're just going to focus simple, and we're going to look at carbons and hydrogens, and that's it. But there's another criteria. This is number one. It has to be a hydrocarbon. And number two, it has to have nothing but single bonds. That's it. So if you're drawing Lewis structures for these, or if you see structures for these, and you see like a carbon that has a double bond carbon, or you see a carbon that has a triple bond carbon, those are off limits. Those are not called alkanes. Those are called something else. So we're very specific. Alkanes have carbon and hydrogen only, and they only have single bonds. And if it meets those two definitions, we have an alkane, and we need to learn how to name those alkanes, and we need to learn how to draw those alkanes as well. Now, in the world of alkanes, we have some other words that we like to use. So we're going to build our vocabulary a little bit. And one is called saturated, and the other one is going to be called unsaturated. The world of alkanes, that is a saturated molecule or a saturated hydrocarbon. So remember, I said we like to sound smart, and in the last maybe minute or so, I told you that alkanes have to have single bonds. Okay, well that doesn't make us sound as smart. So what we like to say instead is that we have a saturated hydrocarbon. See how fancy that makes you sound? I mean, say it out loud. You'll impress yourself, I think, if you say that. So saturated hydrocarbon basically means that carbon has 4 bonds, and those 4 bonds are all 2 atoms. There is no double bond, and there is no triple bond that's involved. It really does have 4 bonds, and they're all single, and they're all connected to another atom. Those could be other carbons, they could be other hydrogens, it could be, in the world of alkanes, it's about it. But this is what we call a saturated hydrocarbon. An unsaturated hydrocarbon would be a carbon double bonded or a carbon triple bonded. What this means is that carbon really doesn't have 4 things attached to it. I know it has 4 bonds, but it doesn't have 4 things that are attached to it. It's a different way of looking at things. So in the world of alkanes, we are focused in on the saturated hydrocarbons only. We are not focused on the unsaturated. That will come later. That will come in a different lecture module, or maybe 2. But we're only focused on saturated at this point. Now, we have another term. You probably would realize that. It wouldn't surprise you at this time. And if we don't want to call saturated hydrocarbon, because we didn't want to use the word single bonds, then we can also use the word called aliphatic. It means the same thing. Aliphatic kind of goes back to the word fat. I mean, you can actually say aliphatic in that term, fat, right? Fat aliphatic. So aliphatic really kind of transfers over to fat-like. Well, this really kind of has tendencies to describe the way these compounds react. These compounds are very much what I would call like oil. Oil and water don't mix. And most of these saturated hydrocarbons, most of these aliphatic groups or molecules, they do not mix with water. They are fat-like, they're oil-like. So they're not going to be miscible with water, which means they're probably going to be nonpolar. They're not going to have groups on them that carry full-blown negative charges that can dissolve very well in water. You know, polar and nonpolar, they don't mix. So the whole world, again, is completely different than general chemistry. We are not basing things on an aqueous environment here. It is more organic, and they dissolve very well in organic solvents. So compounds of organic react very well together, but they only stick to themselves. They don't really socialize with other groups of compounds that are out there. Something else that we can throw out as far as term goes as well is the term acyclic and cyclic. And folks, both of these are okay in the world of alkanes or saturated hydrocarbons or aliphatic compounds. So acyclic and cyclic, well, you can kind of probably predict. It's not going to take, a rocket scientist here to figure out what those terms mean. Cyclic means a circle, right? So sometimes we have compounds that are kind of like snakes. And these snakes can just wiggle on. There you go. I'm not drawing it the proper way, but they do give a nice little wiggle, a little curve, and they're more straight as can be. And those are called acyclic compounds. However, the head of the snake can turn around and bite its tail. So what that means is that sometimes this wiggle is actually long enough for it to wrap around and connect back onto itself. So we have these cyclic compounds that can form as well in organic. And we're going to have to learn how to draw both, and we're going to have to learn how to name both of them as well. So that's very important. Okay? All right. So with that said, let's take a look at an example problem. Before I do that, though, look, we almost had a crash. And we did have a crash. My microphone fell to the floor. Okay, so what we were discussing is before we go to an example problem, there is a template that I like to provide with the alkanes. And it just really sums up all the definitions that we've talked about so far. And the formula for an alkane is going to be CnH2n plus 2. All right, so this is what I would call an equation, if you want to think of it as an equation, but it's just a very quick reference point. If something is going to be classified as an alkane, then it has to meet this template. So what this means is that N equals a number. Okay, let's say 2. So let's say that we had 2 carbons that were involved. In order for this to possibly be an alkane, notice I said possibly, if it was possibly an alkane, then what I would do is I would calculate the amount of hydrogens that it would take. Well, 2 times 2 is 4, plus 2 more, well, that's a total of 6. So if I had a compound that was C2H6, then this possibly could be classified as an alkane, which means it's carbons and hydrogens only, and it's all single bonds all the way across the board. Well, some of the very simple, early, smaller molecules, we can kind of do this ourselves. We can just draw these out and count the number of hydrogens. That's not going to be a problem. But, folks, the problem with organic is that there's, hundreds of thousands of compounds. And because of that, what we have to do, we have to get ourselves prepared with larger, bigger structures. So let's say that we had 60 carbons instead. Do you want to draw out 60 carbons? Do you want to draw 60 carbons on a sheet of paper and draw 4 lines to each one of them and then connect all the carbons together and connect all of the hydrogens together? No, I don't think so. Okay, that's going to be a pain. You'll be there for hours. Nobody wants to do that. But I can quickly use this equation, if you want to call it an equation, to figure out how many hydrogens that I would need in order to make this meet the definition of an alkane. So if I had 60 carbons, in order to calculate the number of hydrogens, I do 2 times 60, because it's 2n. So 2 times 60 is 120, plus 2 more. So this is going to be 122. All right, so that's how I use that template, CnH2n plus 2. All right, so let's look at an example problem. Here's one, maybe came straight from your textbook. And part A says, how many hydrogens does an alkane with 17 carbons have? All right, well, this is using that template that we just talked about. And I can sit down and I can draw 17 carbons and I can connect them all together. And then I can put as many hydrogens to make them all happy. And then I can count the hydrogens up. Or I can say, oh, well, okay, C, 17, and H. Okay, well, 17 times 2, if you need a calculator, well, you're more than welcome to use one, but you can probably do that into your head. So 17 times 2 plus 2, what do you get? Well, if you said 36, you're correct. Good job. You just answered the first question of the problem. See, nobody said organic was hard. All right, and then part B. Part B says, how many carbons does an alkane with 74 hydrogens have? Oh, they're trying to get tricky now. Here, they are giving me the number of hydrogens, not the number of carbons. Well, it doesn't really matter, people. You know, I mean, I use the same template. There's no difference in it, okay? So it's telling me that the number of hydrogens here is 74. So that means 2n plus 2 has to add up to 74. That's how we got that number. So I'm going to solve this equation, make a math teacher happy. Subtract 2 from each side. You do the opposite of. You get rid of everything else around the variable first, and then you worry with the variable. So I need to get rid of the plus 2. Do the opposite of, subtract 2. So 2n is equal to 72. And then this is 2 times n. So do the opposite of multiplication. So that means divide. And we're going to divide by 2 here. All right, so if you need a calculator, pull out one, do the calculation. I don't care. This isn't a math class. I'm not testing your math knowledge. I just simply want the answer to the number of carbons. So 72 divided by 2, or if you can do it in your head, what do you get? Well, if you said 36, congratulations, you got the right answer. So there's our first example problem that we are seeing in the organic lecture. So don't be surprised if you see these on the online assignments. These are very easy questions that Blackboard will come around with. And the reason is because it requires a number only, and it does a very good job with those. But keep in mind that Blackboard really has complications with drawing structures. So as we get later and later into this lecture, you will probably often hear me say, on the assignment that you're going to have to do, on the assignment that you'll have to do, on the homework assignment that you'll have to do, and that's where these questions will come into play. Anything that you have to draw, anything that you typically will have to do on a sheet of pen or a piece of paper and a pen that can't easily be adapted into Blackboard, you're going to have to manually do those yourself and then scan that document up into the Blackboard system for me, so that way we'll know. All right, so the answer to A is C17H36, and the answer to B is C36H74. All right, so let's kind of get to it, right? So this was our first problem in organic. And folks, we're just going to push into the pool, all right? So we're going to start this building up process here. And we're going to start off with 1 carbon, so we need to learn how to name, right? That was the whole slide a couple of minutes before. And this carbon has 4 bonds that are attached to it. That's the only way that it can be an alkane. And then we're going to add hydrogens on each one. So there you go. Now we have to name this organic molecule. And that's where this video is going to stop. So in the next video, we're going to pick up from here. We're going to take this molecule with this one simple little carbon, and we're going to learn how to name it. And this is going to be like learning a foreign language, because it kind of is. I mean, all of these are terms and words that probably we did not have in our vocabulary first, and that's fine. That's part of organic. We're blending in a little bit of science with a little bit of foreign language, and we're starting with the foreign language aspect of it first. So we're going to take this in baby steps, and then the next video we'll pick up from here, and we'll continue to talk about naming, and hopefully we'll get your procedure down in place. So come back. Don't take a break on me yet. If you need a water break because I've already worked you up into a sweat, then go take one, but I'll be here waiting when you get ready.